Here is again our definition of changes of thermal energy. So far, we only dealt with the changes of kinetic energy of particles within an object, and we were able to quantify that change of thermal energy by measuring a change in temperature. Work done by conservative forces between particles within an object can also contribute to a change of thermal energy. Potential energy changes are related to changes of spatial arrangement of the particles within the object. Chemical reactions are an example of changes in spatial arrangement, but we will leave those changes of potential energy to a chemistry course. The difference between a solid and liquid form of a substance also involves a change in spatial arrangement of the particles. So does the difference between the liquid and the gas form of a substance. Take, for example, 1 kilogram of a substance in solid form in constant contact with a large object at a much higher temperature, a burner, for example. We will follow the progression of its temperature as it keeps on receiving heat from the much hotter object. At first, the solid increases its temperature from the temperature it had before the contact with the hot source of heat. The increase in average kinetic energy of the particles will eventually make the particles freer from each other, and the substance starts to melt. Progressively, more and more of the substance is transformed from solid to liquid, but during this process, the temperature does not change. The temperature is called the melting point, and it varies with the substance. During the melting, the substance is still receiving energy from the hot object. This energy does not provide a change of internal kinetic energy, but is a change in internal potential energy. Once the whole substance is in liquid form, the temperature of it starts to rise again until it reaches the boiling point. At this point, the substance changes again, but from liquid to gas. During that transition, the temperature stays constant. It will start rising again once the liquid has all evaporated. While an object is melting, it is increasing its thermal energy due to a rise in potential energy. The more mass there is to melt, the more heat is required. This simple insight leads to this equation. Q is the heat required to transform a solid substance of mass m into its liquid form. Lf is called the latent heat of fusion and depends on the substance that the object is made of. For example, the value of the latent heat of fusion for water is 334 kilojoules per kilogram. A similar equation is required for the transformation from liquid to gas. The only difference is in the value and the variable name for the energy per mass required to vaporize. This constant is called the latent heat of vaporization. For water, LV is 2.26 megajoules per kilogram. Notice how much bigger is the amount of energy required to vaporize 1 kilogram of water compared to melting it. Here is a simple numerical problem involving one of the equations that was just described. We want the value of the energy required to melt a lead ball. We are given the latent heat of fusion for lead and the mass of the ball that we can convert in kilogram. Since we want the energy to melt the ball, we will use this equation. Substituting the givens gives that, and the result of the multiplication gives this value. 0.13 kilojoule is our final answer. Now on to a more complicated example. You are mixing an ice cube into liquid water and wait until a temperature equilibrium is reached. You are mixing something at minus 15 degrees Celsius and something else at 5 degrees Celsius. So the equilibrium temperature will be between minus 15 and 5 degrees Celsius. We are faced with three possibilities. Either the equilibrium temperature will be below, at, or above the melting point. If the equilibrium temperature is below the melting point, all the water will be frozen. The ice cube would have seen its mass increased by the mass of the water. For our example here, that would be a mass of 208 grams added to the initial 75 grams, giving a final mass for the ice cube of 283 grams. If the equilibrium temperature is the same as the melting temperature, then the ice and water can coexist since they have the same temperature. The last possibility is that the equilibrium temperature is above the melting point, in which case all the ice has melted, and the final mass of the ice cube is 0. The trick to solve this problem is first to ascertain which of the 3 possibilities we are dealing with. Let us set the givens. We have the initial mass of the ice, the initial temperature of the ice, the initial mass of the water, and the initial temperature of the water. We will need some constants that could be found in data tables or that were mentioned in previous lectures. We need the specific heat capacity of ice, the specific heat capacity of liquid water, and the latent heat of fusion of water. We also need to recall the temperature at the melting point. This can be read as the fusion temperature or, in some calculation, as the final temperature, like in the case of the second possibility. Let us get a feeling for the size of the change of internal kinetic energy when the temperature of the ice is increased up to the melting point. The equation involved in this calculation was discussed in previous lectures. Substituting the givens and using a calculator gives this. Similarly, we can evaluate the change of internal kinetic energy necessary to bring all the water to the freezing point by using this equation. Substituting the givens and multiplying these values gives minus 4.4 kilojoules. How does this information help us to decide which of the possibilities we are dealing with? If the energy required to bring the ice to the melting point had been higher than the energy lost by the water to do the same, then part of the water could freeze, because energy would still be transferred from the water to the below freezing ice. The water could do so by lowering its internal potential energy, i.e., by freezing. However, if the heat released by the water is exactly equal to the heat necessary for the ice to reach the melting point, then both the ice and the water reach the melting point at the same time, and no further transfer of energy occurs. The ice would not increase its mass, and the equilibrium temperature would be at the freezing point. But if the heat gained by the ice to reach the melting point is smaller than the heat lost by the water to reach the melting point, then the ice at the freezing point will find itself floating in water above the freezing point, and further energy transfer would require the ice to melt. Possibility number 2 or 3. Looking back at the numerical values for Qi and Qw, i.e. 2.3 kilojoules and minus 4.4 kilojoules, we can see that we are dealing with the third situation, where some of the ice will melt. Now that we know that we are working with a situation where some of the ice will melt, we have to evaluate how much mass will be lost to the melting. Will it all melt, which is possibility number 3, or will only part of the ice cube melt, which is possibility number 2? Let us see if possibility number 2 is physically possible. Let us define the variable Qp as the heat in relation to the melting of some ice when dealing with possibility number 2. By conservation of energy in an insulated container, the sum of all the changes of energy must add up to zero. For the possibility number 2, it means this equation. If we isolate for Qp, we get this. Since Qp is the heat received by some ice that melted, we can write this equation, where mm is the mass of ice that melted. Isolating for mm gives this equation. Now, remember that this equation is set up for the case where the equilibrium temperature is at the melting point. If evaluating mm leads to a value higher than the initial mass of ice, we have to discard the possibility number 2 because there would not be enough ice at the start to use up the energy released to bring the water to the freezing point. Let us evaluate the mm with our numerical values. At 6 grams, mm is smaller than the initial mass of the ice, which was 75 grams. Thus, possibility number 2 is consistent, and we can get the mass of the ice at equilibrium by subtracting the mass melted from the initial mass. Using our numerical values, we get a final answer of 69 grams. We first discussed energy in relation to macroscopic solid objects, such as their kinetic energy and their gravitational potential energy. We then look at the energy inside these objects and related that energy to temperature and the spatial arrangement of the particles within the object. This was the subject of thermal energy, which involves averages of the energy of a large number of atoms and molecules. We next need to look at the concept of energy at the level of the nucleus of atoms. However, before we do that, we need to define the symbolism used when working with nuclear reactions. This will be the subject of the next installment.